let us know when we should get started.
I think we are ready to start, but we need to wait for the participants to come. So whenever someone comes, then let's start. 네, 들어오신 분들 중에서 저기 챌린지나 무슨 IonQ 사용에 질문 있으신 분은 질문을 해주시면 되겠습니다. 오늘은 저기 워크숍이 아니고요. 오늘은 그 챌린지에 대한 그 질의응답하고 그 다음에 뭐 Dennis, is it kick off today? No.
No,
Today is the off hour, right?
we kicked off last week, so this is office hours.
We don't repeat the kickoff again, right? So, yeah, 네, 오늘은 그 질의응답 시간이기 때문에 들어오신 분들 중에 질의응답이 있으면 자유롭게 하시면 되겠습니다. Dennis, so, yeah, you have the opening remark, maybe.
Okay. So, Sang is going to translate, but I wanted to thank everybody for joining us today. And I have here the people that wrote the problems for the challenge. And we wanted to be available to answer any questions that you might have.
예, 오늘 오신 여러분을 활용하고요. 저희가 오늘 이 챌린지와 관련해서 질문하고 싶으신 것들을 대답하기 여기 있습니다. 그래서 챌린지에서 질문하고 싶으신 부분들에 대해서 언제든지 질문해 주십시오.
Can I ask something?
Please.
I have a question about the challenge number 3. If we see the task 4, the Hamiltonian is constructed by a tensor product of Pauli matrices. But if we see the task 3, as I understand, the notation is a simple matrix multiplication, like x, 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 y, not tensor product. So could you let me know more clear understand, like a tensor product of xx and xy, or x or xx and y, such like things. Could you let me know?
I believe Luning, you can clarify, but looks like task 3 should have been a tensor product, not just a simple matrix multiplication.
Right. So they should be. It should all be tensor product, not simple matrix multiplication. And then do you want to clarify the difference between these two, or that's enough?
I want to know the tensor product is 한국어로도 될까요?
네, 그렇게 해주시면 일단은 여기 다른 분들 위해서 제가 여기까지 내용만 좀 translate 하도록 하겠습니다. 다른 분들. For others, let me translate so far up to now. So the question was asking the difference between tensor product and simple matrix multiplication, and he wants to ask like the more clear description or explanation about like tensor product compared to the simple matrix multiplication. Yep. 그리고 한국말로 물어보시면 제가 그 질문을 통역하도록 하겠습니다. So he's going to ask in Korean and I'll translate. Yep.
Got it. Thank you.
이제 그 문제 태스크 3를 보시면은 이제 뭐 exponential i의 tau xxxy를 구하라고 했는데, 이제 x 텐서 프로덕트 x 텐서 프로덕트 x 텐서 프로덕트 y인지 아니면은 x 텐서 프로덕트 x 텐서 프로덕트 xy인지 이게 구분이 안 가서 첫 번째 x 오로지 첫 번째 x, 첫 번째 큐빗에만 작용하는 건지 아니면 xx 앞에 xx가 첫 번째 큐빗에 작용하는 건지가 모르겠어서.
네. 그러니까 질문이 이게 x 텐서 프로덕트 x 텐서 프로덕트 y인지 x 텐서 프로덕트 x 텐서 프로덕트 y인지 아니면은 x 텐서 프로덕트 x 텐서 프로덕트 xy인지. 그래서 이 x 텐서 프로덕트 x가 첫 번째 큐빗에 작용되는 것인지 그것이 좀 명확하지 않다는 말씀이시죠?
네.
Yeah. So the question is about like in task three, there's like a X tensor product X tensor product Y. He's unclear about it's X tensor product X tensor product X X tensor product X tensor product Y, or is it X tensor product X tensor product Y or XY? So like and also the first two the first part of this tensor products, which is X tensor product X, is applied to first qubit, or it also applied to first and second qubit. So he's unclear about like the term, or can I say the representation of tensor product described here, and also X tensor product X is applied to the first qubit or others. Does it make sense? And yeah.
Yeah, makes
So
sense.
now,
Luning,
how much can we share? Can we say about it to like make sure the problem still like has its own difficulties, so that we don't just give out the answer?
I understand the concern. Maybe Luning, do you have access to overleaf file?
I should.
Yeah, it's just that I only have cell phone right now because, as you can see, my power's out.
Yeah, let me log into that.
Yeah, and then perhaps we could clarify the definition of tensor product. Yeah.
So you mean like the? Yeah, I can pull the like the the problem. Can someone enable?
If you can share.
Can I need to someone need to enable me to share.
예.
Okay.
우선
You're
이
enabled. You're
문제를
enabled.
예.
Sorry.
예, 우선 이 문제를 저희가 쉐어하도록 하겠습니다.
Yes. Okay. So I believe this. Yeah. So this part, right? So now, and then so essentially, like they're asking like if this X, Y, and then what is actually this tensor product applying to, right?
Yeah,
Okay,
right,
so
that's correct. Yeah.
So in this case, I believe, so if you look at this this particular term X, Y, and it is actually tensor product X, so it's a tensor product X, tensor product X, tensor product X, and tensor product Y.
Yeah.
And then
yeah, let me translate up to this part.
okay.
예, 여기서 보게 되면은 이것은 사실 X tensor product X, tensor product X, tensor product Y입니다. Yeah, go ahead, please.
Okay, and then so regarding like which like X acting on which qubits, it's really like a your own choice, or so this is just like a general like frame saying that you can see terms like this. So it could be like this Y is acting on the first qubits, and this X is acting on the space of the second qubits, and then this one is acting on the space of third qubits, and then this one is acting on the space of the fourth qubit. But it really depends on like how you do the Jordan-Wigner transformation, and then you can either like have a different terms, like if you do the Jordan-Wigner transformation differently, you can have like Y acting on the last qubits, and X acting on the second to last qubits. So it really depends on how you order like your qubits and how you do the Jordan-Wigner transformation.
You mean total transformation? That's what you said, right?
No, Jordan-Wigner transformation.
I'm sorry. Could you say it again? Which one?
The Jordan-Wigner.
Jordan. I see. Yeah,
Yeah.
I see. Right. 여기서 X tensor product X, tensor product X, tensor product Y인데 이것이 어떤 큐빗이 어디에 적용되는지는 철저하게 여러분들이 결정하시는 부분이고, 예를 들어서 일반적으로는 뭐 Y가 첫 번째 큐빗, 마지막에는 Y가, 그리고 그 앞에 있는 X가 세 번째 큐빗, 그 다음에 있는 x가 두 번째 큐빗, 그리고 가장 왼쪽에 있는 x가 첫 번째 큐빗으로 할 수 있는데, 조던 JWT 이 트랜스포메이션에 따라서 여러분들이 이것에 바꿀 수도 있습니다. 예를 들어서 y가 네 번째 큐빗에 적용되게끔 할 수도 있고, 그건 철저하게 여러분들이 이 트랜스포메이션을 어떻게 하는 거냐에 따라서 이 부분들을 결정하실 수가 있습니다. 예.
Yes, I think this will clarifies itself once you start to do the Jordan-Wigner transformation, and then you'll be able to look at to actually see what the terms looks like after you do it, and then it's what clarifies it.
예. 이것은 여러분이 직접 이 JWT를 실제로 적용해 보고 그 텀들을 보게 되면은 이것이 더 명확하게 보이실 것입니다.
Did that answer the question, Sang? Or
잘 답변이 됐습니까?
네네. 감사합니다.
예. Thank you. What he says.
Saying there was a question in chat.
Oh yeah, actually it's not a question, like it's some sweet word, like because last week he spent most of the time working on his graduate paper, so he couldn't have a chance to work on challenging, so I'm saying sorry about that.
Okay.
It's very sweet. Yeah,
That's very nice.
yeah.
Any other questions? Well, why don't we go through the problems? Are there any questions on the first problem?
첫 번째 프로그램에 대해서 혹시 질문 있으십니까? I don't think they have. Yeah.
Okay, or the second problem?
네, 두 번째 질문 있으십니까? No. It's like, yeah. 질문 있으십니까?
Can I ask one more thing?
Please.
Yep, sure. Yep.
If we see the Hamiltonian, there's only two correlated two index sites, such as 1 alpha and 2 alpha, or 1 beta, 2 beta. But how can appear the Hamiltonian form such as XX, XY, which acts on all 4 qubits? 4 qubits.
I don't quite understand that question. Are you asking like if you see like there are terms like XX, so like only acting on 2 qubits, but we have like a 4 qubit Hamiltonian. How does that work?
Yeah.
Okay. You say you can, if you see terms like that, you can assume that the rest of the qubit are acted by identity matrix. So like XX could be like XXII, or XIIX, things like that. So so this will clarify itself if you actually do the Jordan-Wigner transformation and then look at the terms, and then you'll be able to see like which one is acting on which qubits, and then there are terms in which like there are 4 tensor product of 4 Pauli matrices, and then they're acting on 4 qubits non-trivially, and then there will be terms like only 2 matrices acting on 2 qubits non-trivially, and the other 2 are just identities. So they correspond to different terms in the actual Hamiltonian. So you can imagine like the non-correlated term, like the kinetic energy terms, will correspond to like a less like a number of Pauli matrices acting on qubits, but then the correlated terms like the Pauli repulsion terms were resulting in like a more dense of this tensor product acting on all qubits.
So let me clarify the Let me clarify the question. So question was like we have only XX or XY, then how can we act on 4 qubits, right? Is that the question? Yes. Okay. 질문은 XX, 우리가 예를 들어서 이제 해밀토니안 그 문제에서 XX 혹은 XY가 있을 때 이것이 어떻게 4개의 큐빗에 할 수 있는지에 대해서 질문이었는데, 이제 루닝 박사님의 답변은 이제 non-trivial하게 2개의 큐빗 XX는 그렇게 되지만 트리비얼한 것에서는 뭐 아이덴티 매트릭스라든가 이런 걸 사용해서 뭐 XXII 혹은 XIIX라든가 이런 걸 이용해서 4개의 큐빗으로 할 수가 있고, 그리고 Luning, can you repeat once again the latter part of your explanation? I missed that. Yeah. Oh, sorry.
Yes, so the later part is that I'm saying different of these Pauli matrices or tensor product of Pauli matrices will correspond to different terms in the Hamiltonian.
Mm-hmm.
And then you can imagine like a non-correlative terms like the kinetic energy term will correlate, will like after you do the transformation, it will give you something that only involves like 2 like tensor product of 2 Pauli matrices that acting on 2 qubits non-trivially, and then like the actual correlated term, like the Coulomb energy terms in the Hamiltonian, it will more likely to give you a Pauli matrices tensor product, the Pauli matrices that act on all qubits, like entangles all qubits. So.
그러니까 이 그 두 번째 부분은 이제 우리가 폴리매트릭스의 텐서 프로덕트에서 이제 텀들 중에서 이제 non correlated 텀 혹은 non trivial 텀들이 있는데, 그것을 트랜스폼했을 때 이것에 대해서 이런 non trivial 매트릭스가 나오게 되고, 그리고 제가 그 뒷부분은 제가 이제 생소한 분야에서 좀 잘 이해가 좀 되지 않네요. 혹시 궁금한 부분 있으시면 다시 한번 질문해 주실 수 있습니까? 제가 그 부분에 스페시픽하게 좀 물어보도록 하겠습니다.
아까 제가 질문한 거 말씀하는 건가요?
네, 맞습니다. 예.
그러니까 지금 해밀토니안의 텀을 보면은 최대 이제 2개의 큐빗만 이제 오퍼레이팅이 되는 것처럼 보여지는데, 뭐 가령 예를 들어서 2알파와 1알파에만 작용한다던가, 아니면 1알파와 1베타에만 작용한다던가, 그런 식으로 2개의 큐빗에만 작용하는 것처럼 보이는데, 어떻게 이제 XY처럼 4개의 큐빗을 한꺼번에 작용을 한 오퍼레이터가 나올 수가 있는지 아무리 트랜스포메이션을 해도 네, 그런 부분이 좀 궁금했었습니다.
그러면은 지금 질문에 답변이 잘 됐나요? 아니면 그 뒷부분이 지금 잘 전달이 잘 안 됐나요?
사실 질문의 의도가 좀 달라진 것 같습니다. 제가 영어 실력이 안 돼서. 네네.
네네. 그러면은 혹시 다시 물어보실 수 있으신가? 아니면 그냥 이렇게 뭐 괜찮으십니까? 아니면 다시 물어보시면 제가 다시 질문하도록 하겠습니다. 예.
제가 한번 다시 혼자 해보겠습니다.
네. 네, 알겠습니다.
감사합니다.
네, 감사합니다. 네.
Saying, is everything good or?
Yeah, I mean, he's going to spend a little bit more time about like elaborating the question. So like, yeah. He said a little bit, he needs a little bit more time. Yeah.
Yeah, not a problem. Whenever he's ready, we're happy to try answer. Yeah, no problem.
So saying, can you ask them if they think the questions are easy or hard, or any comments on the questions?
Sure. Yeah. 혹시 지금 저희 이 프로그램 질문들이 혹시 좀 피드백을 좀 주셨으면 좋겠는데, 이게 쉬운지 뭐 아니면 중간인지 딱 적당한지 아니면 좀 어려운지 피드백을 좀 주시겠습니까? 어떤 피드백도 괜찮습니다. 예.
그 문제 한국어로 해도 될까요?
네네. 네.
네. 약간 문제가 쉽고 어렵고를 떠나서 되게 혼자 공부할 때 양자 컴퓨터에 대해서 공부를 할 때 굉장히 도움이 많이 될 것 같아서 정말 감사의 말씀을 드리고 싶습니다.
네. He would like to say thank you because like it was really helpful. I think it would be really helpful to learn detail about the quantum computer, whether or not the problem itself. Problems are like the hard or easy to solve. So it was really helpful, like to study this problem and try to challenge this problem and try to solve it. Yeah, so it's really helpful, and thanks for this opportunity. Yeah.
Thank you.
Okay. So we will be back again next week if they have any questions. And
Dennis,
yeah,
I found there was one email to us that he found the one typo in the problem. So let me share my screen.
okay.
Please.
Who made the typo?
It's probably me.
So-
Oh my god, because I am good at making typos.
So the rotation operator here is it is not unitary, so there should be minus the I sign. I'm just comparing with the like Wikipedia page, and the RY is also they put the minus sign here. Not, do you see my cursor?
Yes,
Monster?
I see it.
So, and this is plus sign, and typically people just divide by half, right? So when there's 2 pi rotation, it is in the same identity operator with the -1, like over phase. So let me compare it with the this logic gate. So every theta here is like divided by 2. So when there's 2 pi rotation, it's just like it means the rotation in the plus pair. Yeah. So I think the these Rx is obviously something wrong. ry theta. It could be just like the differential angle, like direction.
Oh,
And,
yeah.
yeah. These like these two doesn't have like 1/2, while this one has 1/2. So we should like make it consistent to each other.
I can fix that and send it to you. Is that an option to update or?
Yeah, we can update. And why don't you just share us the overlay link so I can
did not share the overlay with you. I will share that with you. Yes, not a problem.
Please do both of them. Yeah.
Yes.
Thank you.
We'll get that done as soon as we're done with the call. And yeah.
Okay, that's it. Thank you.
Thank you.
Yeah, I think if there's no question, we can wrap up today's session. 혹시 더 질문 있으시면 말씀해 주세요.
혹시 질문 하나만 드려도 될까요?
예, 말씀해 주세요.
My question is on problem 3. And in the problem, it says that we can see tensor products of Pauli matrices such as XX, XY. But in my calculation, I couldn't see 4 products of Pauli matrices because the Hamiltonian does not have 4 products of different sites. I mean, the last terms, for example, 1 alpha, 1 beta terms, looks like to have 4, but it's just regarding only 2 sites. So my question is how we can find 4 tensor products.
Actually, I have the same problem with him.
Yeah, this is the same question with D1.
Okay.
Yes.
And it was not like fully answered, I guess. So yeah. So the question here is just like we only see like connection between Hoppington between single site, while the you suggest there should be like 4 Pauli matrices term in the Hamiltonian, and why we should expect that.
And actually, moreover, I couldn't see XY terms because it symmetrically disappears. So in my calculation, XX and YY terms are on the left. So can you please answer about this too?
Okay. I think I understand the question. Luning, is there a typo in Hamiltonian expression equation 5 and overleaf?
Equation 5. So I think X, Y are expected.
No, equation 5, the Hamiltonian of the system is blah, blah, blah. And let us take a look at the product of 4. It's 1 alpha, 1 alpha, 1 beta, 1 beta.
Right. So I think the XY terms should come from like the hopping term, right? I think that's expected. So the XXXY term may actually not be there because we only have because this Hamiltonian only contains this so-called number operators, right? So there's no like operator that breaks the number operator. So I think that's also expected. So because if you have number operator, you can really treat them as bosons, right? And then so I think, at least I think the XY terms are expected, and it's possible that you don't actually see this XXXY terms. Yes, so that's why I put it. You will see terms like these terms, but may not exactly be these terms.
Okay, so I will try my calculation again. But in the task 3, you're explicitly want us to make the gate circuit to simulate XXXY term. And so should we do this or not?
What do you think, Nam? I think doing that is still a good like test for understanding the problem, right?
Yes, I mean,
okay.
test 3 does explicitly say draw the quantum circuit that implements two different things. Matter one x, 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 y. So yes, even though it may not necessarily appear in connection with the Hamiltonian, the task is pretty clear. It should be drawn.
Okay, thank you. And are there some set of gates that we are allowed to use or not?
Well, I think you're afraid to use any gates.
Yeah, any gates are fine.
Yeah.
Yeah.
Okay, thank you very much.
Yes.
And also, I have some question on problem 1. Is it possible to ask now?
Yes.
Okay, so from the task 1 to 4, are we allowed to use some ancilla qubits?
Yes. You're free to use ancilla qubits.
In the whole problem?
Unless otherwise specified, you're free to use ancilla qubits.
Okay.
Yes.
Thank you.
Yeah.
Actually, the student Hyuk-jun Kwon is coming, who is the one raised the question about the rotation operator.
Okay. Yeah. Sounds good.
Maybe you need to explain again.
That's not a problem. Yeah. I'm actually making changes in the overleaf right now.
예, 권혁준 씨, 아까 로테이션 오퍼레이터에 대한 질문을 우리가 이미 한번 다뤘었어요. 아까 있었었나요?
네, 이제 들어왔습니다. 죄송합니다.
아니에요. 그거 잠깐 서머리 다시 어떻게 했죠? 아까 고쳤죠?
예,
질문을 다시
고치기로
한번-
해가지고 업데이트 하겠습니다.
네. 네, 어떻게 고치기로 했는지 권혁준 씨한테 조금만 설명해 주면 좋겠네요. Could you explain briefly to Hyuk-jun how you are going to fix it?
Yes. We're gonna fix it with the standard definition. Sorry, there were typos. Firstly, there were divided by 2 missings in Rx and Ry definition in the argument of cosines and sines. And the signs were placed incorrectly. So thank you for catching that. Yeah, I was in charge of going through the whole thing and making sure there's no typos. So the responsibility is with me. And yeah, I will fix it and send it over to Junki and we will reshare.
Thank you for your notice.
Thank you. Thank you. Junki, I just shared the overleaf with you. See if you can access it.
Got it.
Awesome. Oh, we also probably need to change it in the translated version, yes?
Mm-hmm.
Yes, let me try that.
Please send me the link for that too.
Yep, will do.
There's one question in the chat window. Hello, I'm Lee Ho-jun, participating this quantum challenge, and I have a question when I'm solving the problem number 1. In number 1.3, it says the score is calculated by cost minus 18, and the score needs to be higher than 3. And in that case, then if the cost is 21, lower than 21, which means like the score is less than 3, then is that accepted or not? Because the circuit I composed has cost of 20.3, and I confirmed this is unitary. So that means the score is 2.3, lower than 3. And second question is, am I okay with like using either big endian or little endian? Like, does it matter? Like either using big or little endian? And third question is, in problem 1 and 2, there are 2 sets of gate set, and do I have to demonstrate all the circuitry out of them? And if so, how the final score is calculated?
Okay, so could you repeat the last part?
In problem 1 and 2, there are 2 types of gate sets, and do I have to show the circuits for both of them, both cases? And if so, then what would be the final score? How the final score will be calculated?
Got it. Okay, so to address, okay, well, I should have taken notes. What was the first part? Was it the score or?
Yeah, score was is the circuitry lower than whose cost is lower than 21 is accepted or not?
It is accepted, but the expectation is that the point is going to be negative, right? Yeah, in the sense that the expectation is that one should be able to find a circuit that has a circuit cost that is lower than 18.
Oh no, what it says is what he asked is like is cost minus 8. The score is calculated by cost minus 18, and his score is 20.3. So still positive, but lower than 3. Non-negative.
No. So it says the point awarded is computed as the difference between the cost and 18. And what you want is lower cost. So the expectation is you want to score, you want to come up with a circuit that has score that is that has a cost less than 18, not above 18.
Oh, okay.
Yeah.
So the score needs to be negative then, right?
Well, I suppose it depends on how one interprets the difference, but yeah.
I see. Okay, so basically the cost needs to be lower than 18. So
Yes.
20.3 is like
It's still above what we
above. Yeah. 예, 1.3번 문제에서 아마 이건 좀 번역이 좀 잘못된 것 같은데 이 점수가 cost minus 18으로 되는데 어쨌든 cost가 18보다 적어야 된다고 합니다. 예. cost가 so the cost needs to be lower than 18, right?
That's right.
I think the translation is kind of like a wrong or kind of ambiguous. I asked this question to you, but maybe I misunderstood. 그래서 cost가 18보다 적어야 됩니다. 그래서 20.3인 거는 이제 그 기준에 맞지 않는다고 합니다. 예.
Okay. And the second question was same.
Is it okay either use big endian or little endian? Do I have to use?
Yeah. So answer to that is clear. In a sense, yeah, you're free to use either, and so long as which endian is used is clearly indicated.
어떤 엔디안을 사용할지 명확하게만 표시가 된다면은 어떤 것을 사용해도 괜찮습니다.
Yeah, and the third question was about the gate set. So what is exactly the issue?
The question is, do I have to show the circuits for both cases?
This was 1.1 and 1.2 or
I think it's 이 문제가 제가 지금 그 오버랩가 없는데 문제 1번과 2번에 되는 건가 아니면 뭐 좀 더 스페시픽하게 얘기해 줄 수 있으신가요?
이거 지금 참석한 문제하신 분이 이메일한 거를 갖다 붙여주신 것 같고요. 1.1번에 1.2번일 것 같은데 2번은 서킷이 안 나올 거예요 아마.
1.1번에 죄송해요. 다시 말씀해 주시겠어요?
I think it is problem 1.1 and 1.2 because we don't need any gate set for problem 2. Although the question says it's like problem 1 and 2.
Oh, okay. For problem 1, which gate set to use is, I believe, clearly indicated for each subtest. So for instance, for 1.1, there's a standard gate set provided in equation 1. And for test number 2, 1.2, the gate set is also provided to be XX gate with angle of rotation being pi over 2, and then RX, RY, RZ gates. So, and for problem number 2, which is the ion trap question, I do not believe there's a gate related question.
Might have been talking about like the subtasks potentially.
Yeah.
Within question 1.
I think so. And regarding to the problem about the 1.3, about the points, I think it's a little bit ambiguous here because he said the point awarded is computed as the difference between the cost and 18. And the last sentence also mentioned with point larger than 3 will qualify. So does it mean the point should be, actual cost should be lower than 15?
Poles solutions with points larger than. In a sense, yes.
Yeah, I think yeah, we should a little bit. How can we clarify this?
Okay, I am.
Why don't we just like the any cost lower than 15 will qualify?
Sure. Maybe I'll read it again. Maybe I myself am interpreting incorrectly. So. Yeah.
Yeah, it's not the like translation problem. The actual English sentence is a little bit ambiguous, I think. Yeah. 네, 말씀해 주세요.
Yes. In the task 5 of the level 3, I think it's non-unitary. And this is because each row of the unitary matrix are not orthogonal.
Which problem is this?
I think the task 5 of the level.
That's 5 of problem 1. 1.5.
Yes, problem 1. I'm sorry.
Could you repeat why it is not unitary?
At the bottom of the row, you can see there are two exponential.
I think there's a type. Yeah.
Yes.
Yeah. Yeah, I believe there is a typo. Let me double check this. Yes.
Oh, thank you.
Yeah.
Yeah, lots of homework for them.
Yeah, I'll fix it. It's pretty clear.
Any other questions?
Yes, may I ask a question to Dr. Luning Zhao?
Luning, you're up.
May I get a help about the Jordan transformation? I have tried to transform the Hamiltonian into Jordan transformed Hamiltonian, but I think the concept of the Jordan transformation is not trivial. So, for example, may I share my screen?
Of course.
Thank you. Okay, so I'm doing Jordan transformation like this way. But if so, the paper you cited says that the Z gate should be added to the left qubits, right?
Can you repeat that?
I'm sorry.
Can you repeat the question?
Yes. So this is the original annihilation operator, and this term should be added to the Jordan transformed operator. Is it right form of the Jordan transformation?
I believe that is correct.
Then I think it's weird, because if this is a 1A, then this one should be here, and this is identity, and this identity. But this term is same with the not Jordan transformed annihilation operator.
So I still don't fully understand it. So what is the question? So this is the same as annihilation operator? What?
Yes. So my question is that whether applying Jordan transformation or not, the annihilation operator of the 1A is same. It doesn't change whether whether transformation is applied or not.
So the Jordan-Wigner transformation shouldn't change the matrix representation of these operators, right? So so I still don't understand. What do you mean it does not change whether you apply or the Jordan-Wigner transformation or not? So what does not change?
The tensor product form, because there is no G gate. I think there is no particle symmetry.
Yeah, so there's no Z gate for this one.
Yes.
So, and that is correct. And what is your?
My problem is that this operator, in the 1A operator, the particle symmetry is not applied, because this is just original form.
Yes, that is correct.
Oh, is it right that particle symmetry is not satisfied?
Yeah, that does not satisfy particle symmetries, because you apply annihilation operator to a system that will annihilate one particle.
Yes.
So it will violate particle symmetry. But you never see this annihilation operator on its own. It's always paired with a creation operator. So that preserves the particle symmetry.
So you mean this one and the annihilation operator preserves the particle symmetry?
Yeah, if you if you multiply, so in the Hamiltonian, like each annihilation operator is multiplied by a creation operator.
Yes.
And then that preserves particle symmetry. You annihilate one electron and you create another one, right? So the total number of electrons stays the same. That does not change particle symmetry. But if you only have the annihilation operator on its own, then it will break particle symmetry. But then that term does not exist in the Hamiltonian, because that Hamiltonian preserves the particle symmetry.
Oh, thank you. And I think I have another question on this task 3. You say that the XY gate will be shown. XY and XXY. But I couldn't find anyone. So do you think I did wrong, or I must find the XY and XXY gate?
So I'm not sure whether the XXXY gate will show, because of the like we only have number operators there. So number operators correspond to Z operators. But I think you will see XY gates because of the kinetic energy part of it.
Oh, okay.
So now, do you agree in terms of that?
Yes.
Thank you for your answer.
Yeah, so it could yeah, so I think so after double checking, so it either could be like a XX, XY, and YX gate, or it could be XX or YY gate. So either could be possible. So it's not necessarily XY. It could be XX, it could be XY, YX, or XX or YY. So
Okay.
yeah, sorry for the confusion in terms of that.
Any more questions or concerns? Jungi, I believe I fixed all the typos as far as I could see on the three things, Rx, Ry, and the unitary just now. Oh, and the power is back.
Yannick, were you going to say something? Yeah.
Yeah. So when everything is solved out, then why don't you wrap up the session today? What do you think, Jungi?
I agree.
Yeah.
Okay, then. Thank you, everybody, for your time tonight and your great questions and finding errors in our document. And we will be available again next week in case you have any more questions. And if you want to email us during the week, feel free to email us with more questions. Sounds good?
Yep.
Awesome.
All right. Thank you, everyone. Have a
Thank
great
you.
day. Thank
Thank
you.
you. Bye.
Bye-bye.
Thank you.